Okay, so we're moving on to section 4, or module 4 in section 1. And this is a really important chapter in Algebra 2. It deals with quadratics. Before we get to those, we have to deal with something that's called a complex number. Okay? So if I say simplify the radical expression square root of 16, we all know the square root of 16 is 4. And that's simply because 4 times 4 is 16. But up to this point in math, we said if we had the square root of negative 16, we would say this is not a real number. Because there is no number that multiplies together to give me negative 16, because 4 times 4 is 16, negative 4 times negative 4 is 16. So nothing really gave us negative 16. We are going to change that. We're going to change that today. So we are going to move on to dealing with what's called the complex number set. Okay? So in the complex number set, we try to make sense of the square root of negative 1. Because if you can make sense of the square root of negative 1, you can make sense of any negative square root. Now we're going to really focus on square roots really in this chapter. So we're not going to deal too much with cubic roots or fourth roots. So really everything will be square roots. So this square root of negative 1, for a long time people said, well, it's nothing we really can deal with. But then it kept coming up. It comes up a lot in physics and a lot in electrical theory. So we had to find a way to try to use this. So we decided, we as mathematicians, we decided to give this a name. The square root of negative 1 we call I, and we call it the imaginary unit. So this I is the first number where I can take the square root of a negative number and get something. And thus we define it to be, it's the first number that I square. So if I square I get negative 1. And you could just see from this expression over here, if I were to square both sides, then I get I squared equals negative 1. So with this kind of idea in mind, we can actually now deal with square roots are negative. So let's look at some examples. So we have the square root of negative 16. Typically, we don't know what that is. But from our product property of radicals, I know this is negative 1 times 16. So negative 1, square root of negative 1, we didn't know before, but now we're going to define that to be I. And so now we're just dealing with the square root of 16. And the square root of 16 is just 4. So the square root of 16 is 4, so this is I times 4, or more traditionally written as 4I. So if I look at the square root of negative 121, I automatically know if it is a negative on the inside, it will have an I. So this is I times the square root of 121. Now you could break this down using our factor tree, but I know 121, the square root of that is 11, because 11 times 11 is 121, so this is just simply 11I. So the negative inside the square root just produces this I on the outside. It just tells us that we have this imaginary unit. Okay, let's look at a couple more. We have the square root of negative 28. So again, the negative is going to produce an I on the outside, square root of 28. So this guy is the one that's producing the I. So now I'll try to simplify radical 28. I'll just use the factor tree. So 28 is 4 times 7, and 4 is 2 times 2. So as you can see, I have a group of 2's, because I'm looking for common groups of 2. So that means I can take a 2 on the outside of the radical. So that would be 2 and the I, because the I we took out because of the negative, and then I'm left with a 7. So 2I radical 7. So again, once you take the I out from the negative, the radical stuff's just like we did in the last chapter. Okay, so let's look at one more. So we have this radical negative 64x cubed y squared. So I know the negative is going to become I, so I'll just take that out, and then this just becomes positive. So I just really want to see what's going to come outside of my radical and what's going to stay inside. So if I do 64, that is 8 and 8. That's 4 and 2. And that's 2 and 2. And 2 and 2. So we basically have 64 as 8 twos, or 6 twos all multiplied together. So I have one group of twos, two group of twos, three groups of two. Now, if you just want to recognize that the square root of 64 is 8, that's fine. But just to kind of keep it consistent. So I'm taking 3 sets of 2 out, and there's nothing left in, because all the prime numbers were taken out. Now, as for the variables, I have x cubed. So if I think how many groups of 2 are there in x cubed, well, there's one group of 2 in x cubed and one left over. And as for y squared, there's one group of 2 in that, but there's none left over. So on the outside, we have 2 times 2 times 2 times x times y times I, and then a square root of x left inside. So I can simplify that, because 2 times 2 times 2 is 8, xy, I, square root of x. Okay, so i's have another very cool property, which is they have a very repeating property, because we know that I is the square root of negative 1, and we said, well, that just means that I squared is negative 1. So I to the squared is negative 1. But if we keep going, there is a pattern. So I cubed is actually negative I. And the proof of that is pretty simple, because I cubed is just I squared times I to the first, but I squared from the line above is negative 1, so I cubed is negative 1 times I, or negative I. And then I to the fourth is 1. But then this property actually continues. So if I go to I to the fifth, it actually goes back to I to the first, or just regular I. I to the sixth will be negative 1. I to the seventh will be negative I. And I to the eighth will be 1. So you can see every 4, it is repeating itself. So if I were to continue, I to the ninth would be back to I. So every 4 powers of I, it actually repeats itself. Now, honestly, most cases we're interested in these two values, I being the square root of negative 1, or sometimes I squared equal to negative 1. But it has a cool property that continues on and on and on. Okay. So we can actually do operations on complex numbers, multiply them, divide them, subtract them, all this kind of good stuff. So we'll look at some ways that we can simplify complex numbers. So this first one says 3i times 4i. Well, you can treat I just like a variable. So this would just be 12i squared. Okay, no problem. But here's the one difference. We know that I is the square root of negative 1, but we more importantly know I squared is negative 1. This is so important. So instead of keeping it as 12i squared, which is the correct answer, I can actually replace the I squared with negative 1. And then 12 times negative 1 is actually just negative 12. So I multiplied two numbers, both with this imaginary unit, but my answer has no imaginary numbers. And it's really because of this awesome property, I squared being negative 1. And when you multiply or you divide, you will use this rule quite often. So this one would be very similar. Negative 3i times 9i would be negative 27, and then I squared. Oh, but again, we know I squared is negative 1. So this is negative 27 times negative 1. Negative 27 times negative 1 is just positive 27. Okay, this problem is an addition problem. So if you remember our stuff from Module 3, when we add things, we just add like terms. So I have 2 and 3, which are the same. So 2 plus 3 is 5. And then we have these things with i's. So 3i minus 8i is negative 5i. I don't replace this with negative 1 because it's not I squared. You can only replace I squared with negative 1, not I. So if I take 2 plus 3i plus 3 minus 8i, I simply just have 5 minus 5i, a different complex number. Subtraction is very similar. In polynomials, we said when we subtract polynomials, we turn it to addition, but we distribute the negative sign. So we'll turn it to addition, but we'll turn the 3 negative, because negative 1 times 3 is negative 3. The negative 1 times negative 2i will be positive 2i. So now we turn the subtraction problem into an addition problem. We can just add them. So 12 plus negative 3 is 9. Negative 7i plus 2i is negative 5i. So this is the difference of those two complex numbers. Okay, let's look and see if we're multiplying them. Multiplying really is just a same idea, but we would FOIL. So 2 times 8, or 2 times 4 is 8. 2 times negative 3i, just pretend it's like an x, so it's negative 6i. I times 4 is positive 4i. And I times negative 3 is negative 3i squared. Now a couple things we can simplify here. We have two things that have just an I, so those are like terms. So negative 6i plus 4i is negative 2i. And then here we have that I squared, which becomes negative 1. Again, I squared is always negative 1. So this can become 8 minus 2i, negative 3 times negative 1, is plus 3. Oh, but now we have these numbers that are both numbers we can add together. 8 plus 3 is 11 minus 2i. So we FOILed to get to this step, but then again, the I squared, we always want to be on the lookout for I squareds because they become negative 1. So here's another FOILing one. So 5 times 5 is 25. 5 times negative 2 is negative 10i. 5 times positive 2i is positive 10i. And 2i times negative 2i is minus 4i squared. Well, this is nice in this case because the i's go away, 10i and negative 10i. So we have 25 minus 4 times negative 1. So negative 4 times negative 1 is positive 4. So 25 plus 4, which is 29. So again, very cool. Two complex numbers multiplied together, but in this case, they turn out to just be a number. Okay, so the last thing we have to do with complex numbers is divide them. Now, we actually divide them very similar to how we rationalized denominators in Module 3. So we have 5 minus 3i over i. So really, I just want to get rid of the i's in the bottom. Just like in rationalizing, we want to know radicals in the bottom. So the easiest way is just multiply by the conjugate of what's on the bottom. So the opposite of I would be negative I. So I'll multiply the top and bottom by negative I. Let's see what happens. So on the bottom I get negative I squared. And on the top I'll distribute this negative I. So 5 times negative I is negative 5i. And then negative I times negative 3i is positive 3i squared. Oh, but again, I've got two I squareds. So I squareds can be replaced by negative 1. So this will be negative 5i plus 3 times negative 1 all over negative 1. So negative 1 is just 1. And then we have 3 times negative 1 is negative 3, and then minus 5i. Now, I switched the negative 5i second, and I put the negative 3 once I multiplied first. That's just a conventional wisdom. You do not have to do that. Just generally, we put the I second just as notation. Okay, last one, very similar. We'll do it just like the radicals. We'll multiply by the conjugate of the bottom. So 1 plus 2i. But then what we'll have to do is we'll have to FOIL on top and bottom. So 5 times 1 is 5. 5 times 2i is 10i. 8i times 1 is 8i. 8i times 2i will be positive 16i squared. On the bottom, 1 times 1 is 1. 1 times 2i is positive 2i. 1 times negative 2i is negative 2i. Oh, so those are going to cancel. And then negative 2i times positive 2i is negative 4i squared. So if I start cleaning this up, I know these two go together. So the top will be 5 plus 18i. Oh, there's an I squared. So that's plus 16 times negative 1. All over 1. These guys will cancel. So this is minus 4 times negative 1. So now on the top I have 5, and this is obviously negative 16. So 5 minus 16 is negative 11 plus 18i over, this is 1, negative 4 times negative 1 is plus 4. So this is over 5. So this is my answer. It's got no i's. You could also write this as negative 11 over 5 plus 18i over 5, just by dividing them both by 5. So a little bit about complex numbers. We can actually deal with these square roots of negative values.